Okay, we're back for part two. So we talked about vertical asymptotes. When you're looking for a vertical asymptote, you want to know where the denominator is equal to 0, where the function's undefined. Now, a horizontal asymptote is going to be a little bit different. To find horizontal asymptotes, what we'll do is we'll compare the numerator to the lead term in the denominator. When we looked at polynomial functions, it was always the first term that dominated everything. Same thing's going to be true in this situation. So really there's three cases that we're going to look at. If the degree of the numerator is less than the degree of the denominator. For example, let's say we had x squared on top, that was the lead term, and x to the fourth on the bottom. First of all, we can simplify that. I could divide that, and what I would get is 1 over x to the second. Now notice that what happens is that there's going to be a 1 up top, so the only number that would change if I plug in values is going to be the denominator. The horizontal asymptotes are what you get as you approach negative infinity and positive infinity. It's the values that come out of that. If I start putting in really small numbers like negative 10, negative 100, negative 1000, what's going to happen is that the 1 is going to stay the same, but these will get very big. So eventually I'm going to have a number 1 over something really big, like a million, a billion, a trillion, which is basically 0. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will always be y equals 0. What happens if the degree of the numerator equals the degree of the denominator? Let's say that what you had was, we'll say 6x squared minus 1 over 2x squared plus 3. First of all, I only have to look at the lead term. So I'm only going to look at 6x squared and 2x squared. That's what's going to dominate. If I reduce that, if I do x squared divided by itself, I just get 1 for these. And so what I get is 6 over 2, which is 3. What this is telling me, in this case, I will have a horizontal asymptote at y equals 3. Now let me show you how this works. Okay, so if we go to y equals, and I type 6x squared minus 1 divided by parentheses 2x squared plus 3. Let's go ahead and graph that. There's the first part of the curve. Now, first of all, you get kind of a funny looking curve here. But notice that what happens, see how it tends to flatten out the graph as you go to the left and as you go far to the right? And it looks like we're approaching the value 3. So that horizontal asymptote is going to be 3 for that. What happens if the degree of the numerator is 1 greater than the degree of the denominator? Now in this situation, we're not really going to look at this very much, but if you had x to the third divided by x squared, you could simplify that to x over 1. That gives you a different kind of asymptote. It's called an oblique. And that would be y is equal to x, which is not going to be a horizontal line. It's going to be a slanted line. And so y equals, let me do this. I'll say x cubed. I'll put something else in there. Let me put parentheses. Let's go x to the third plus 6 divided by, and we'll go x squared. Let's see what happens here. There's the first part. There's the second part. Notice how it seems like there's this invisible diagonal line right there. That's y equals x. That's the oblique asymptote. You're not really going to have to worry about that. All right, so let's look at a couple examples to demonstrate this. The first one, number 4, the degree of the top. There's no x here. That's like x to the 0. So 2x is in the bottom. I'm only going to look at the lead terms. So 4 over 2x. And I can reduce that. That's 2 over x. But as x gets really big or really small, that's going to approach 0. Okay, 2 divided by x. If I just look at that, okay, and I'll go to the table. Let me go back to 0. As x approaches positive infinity, look at what the values are doing. They're getting closer and closer to 0. Because what's happening is your denominator is increasing, but not your numerator. So you're getting 2 divided by really, really big numbers, and eventually that's just going to approach 0. So that would be a horizontal asymptote of y equals 0. Now, number 5, look at the lead terms, 4x, 2x. They have the same degree. They're both x to the first. Now, what we can do is simplify that. 4 divided by 2 is 2. X to the first divided by itself is just 1. So what we get is a horizontal asymptote of y equals 2. Okay, so let me go to y equals. Let me show you. If we put the original problem in there, which was 4x divided by 2x plus 8, let's look at it. There's the first part, there's the second part. Notice again that we're starting to flatten out here, and it looks like it's around 2. So y equals 2 looks like a good answer for your asymptote. All right, the last one, I'm going to change this. 4x squared plus x, I'm going to make that 2x to the third. So I'm going to change the problem. Now we're going to look at the lead terms, and we can simplify that. That will become 2 on top. Now in the bottom here, I'm going to subtract my exponents. 3 minus 2 is 1. Because the bigger exponent's in the denominator, I'm going to keep x to the first in the denominator. But 2 over x, again, that's going to approach 0 eventually. If you plugged a million in here, 2 divided by a million is basically 0.000 and so on. It's basically 0. Now imagine putting in a trillion, and you're going to infinity. Same thing with negative infinity. Okay? So those are going to give you your horizontal asymptotes. Y equals 0. All right, so we got one more problem here. Let's take a look at 7. Graph q of x equals 2 over x plus 3 minus 4. State all horizontal and vertical asymptotes. Well, for vertical, we can look at this. We can get this right away. The vertical asymptote is when x plus 3 is equal to 0, when the denominator is 0. Subtract 3 from both sides. X equals negative 3. That would be the vertical asymptote. So I can draw that on my graph here. Vertical asymptote's negative 3. Now let's go ahead and go to y equals and take a look at this thing. So we'll do 2 divided by, parentheses, x plus 3, and then minus 4. There's a minus 4 after. Let's see how that affects it. Zoom 6. All right, so it looks like the graph, from the left, we're decreasing. We come down. Now that value looks like 1, 2, it looks like negative 3 where that's happening. So I think our vertical asymptote that we graphed here looks good. And then we jump over that imaginary vertical line. We come to here. We decrease again. And notice it looks like there's a horizontal asymptote there where the graph starts to flatten out. Let's figure out where that is. I'll go to the table. Let me come back up here. Well, actually, as your x values get bigger, notice that negative 3.8, negative 3.9, it looks like we're getting closer to negative 4. What about, let me go to the table set here, let me go back to 0. What about as x approaches negative infinity? So it looks like we're decreasing, negative 4.2, negative 4.1s, negative 4.0s. Looks like we're approaching negative 4. So the horizontal asymptote, I don't need to guess on this. Okay, I know it kind of looks like if I count 1, 2, 3, 4, I go down. But x equals negative 4 is my horizontal asymptote. Now, let me go ahead and draw the rest of this. So it's going to look something like this on the left, and it's going to look something like this on the right. We could find the Y-intercept by plugging in a 0. Or if I go to I'll go back to the table. When x is equal to 0, the y value is negative 3.3 repeating. So the y-intercept, okay, actually I should have graphed it a little more down here. The y-intercept is down here. Okay, but this is the general shape of the graph. Horizontal and vertical asymptotes. Vertical asymptote is x equals negative 3. Horizontal asymptote is y equals negative 4. And that is the end of the notes. Let me just jot down one more thing. The vertical asymptote is also telling you the domain. The domain is the set of all x's such that x is not equal to negative 3. And the range is the set of y's such that y is not equal to negative 4. And now we are done with the notes.